Let's discuss the 4 problems from today's Division 2 plus Division 1 round by Nebius, starting with B. I will not retell the statement, I think it's pretty clear. You can read it yourself. Okay, let's solve this problem. First of all, let's visually illustrate for every client, for every patient, the time span in which he can take the vaccine. All the time spans will have the length W. Then let's draw the lifespans of our vaccines. Suppose we have several vaccines, each has a lifespan of length G. Then suppose this patient takes the vaccine in this moment, this patient takes the vaccine in this moment, and so on. If we open the vaccine in time TV, and the patient comes to the clinic in time TP, then let's see in which case the patient can take this vaccine. Of course, it's true if their corresponding segments intersect. Let's see when they don't intersect. It's if time of the vaccine is larger than time of the patient plus the wait time, or if the time of the patient is larger than the time of the vaccine plus the living time of the vaccine. But as W is constant for all patients, let's just rewrite it in such form. Let's call Tp plus W T prime P. So here, let's express Tp as T prime P minus W. Let's move W to the right side. As you see, we have shown that it's not important what D and W are equal to individually. It's only important what is their sum. So if we change W to 0 and D to D plus W, the sum didn't change. It means that we can solve the same problem thinking that W is equal to 0 and D is actually D plus W. And the problem will start to sound like this. The wait times of the patients are now 0, so each patient is a point in time. And each vaccine is a segment of length D plus W. Now we can narrow down the search technique by drawing the answer and then trying to modify it. For example, here I drew some answer. How can I modify it? Well, first thing I can do is I can say that I can always take the first segment and move it to the right until it meets the first point. Thus, we have already shown that the first segment must start at the first point. But to show the full answer, you also need to show which points are assigned to which segment, because no more than k points can be assigned to a single segment. And I claim that if we have assigned p points to the first segment, those must be the first p points. To prove that, we will use the same technique again. Let's suppose the answer does not look like that. Let's suppose we have assigned some number of points to the first segment, which are not the first p points. It means that we have skipped some of the points. Let's show it in red. So it means that in this answer, we have assigned it to some other segment. And this other segment is some future segment because we consider it the first segment. Every other segment will occur later if you go from left to right. But it's easy to show and easy to see that we can always reassign those points in the following manner. We can assign this red point to the black segment and this black point to the red segment. And thus we have changed the answer and we have decreased the sum of indexes of the points that are assigned to the first segment, which means that we cannot apply this change infinite amount of times. If we keep applying this change, then at some point we will arrive into a position where the points that are assigned to the first segment are the first p points. So we know where to start the first segment, and we know which points to assign to it. Of course, we assign as many first points as possible because it wouldn't hurt. So then we forget about those points because they are already assigned and everything is already fixed. And now let's consider the remaining problem. In the remaining problem, we can repeat all the same reasoning. So we know where to start the next segment at this point and which points to assign to this segment. So this leads to a very simple solution. Just go through the patients from left to right and open the vaccine only when you need it. Only when the previous vaccine has ended, I mean all the doses came to an end, or when it expired. Then you open the new vaccine. Let's look at the implementation. Here last is the last person for which I have opened the vaccine. And initially it's the first person. And initially the answer is 1, so it means I have already opened one vaccine. Then I go through all the remaining patients and I see if there are too many patients between this one and the last for which I opened vaccine, or if there has passed too much time, then I open the new vaccine and output the answer in the end. Now you can read problem C. I will also write it down in mathematical terms. You are given 3 numbers, n, x, and p. You need to find such number f from 1 to p that x plus 1 plus 2 plus etc. f is equal to 0 modulo n. Or to be precise, you need to find if such f exists. Okay, let's simplify this statement. And you must have paid attention to the constraints. P is up to 1 billion, but n is up to 2 times 10 to the power 5 in total. And x is up to n. Well, basically you need to solve a quadratic equation modulo n, because this is a variable, an unknown variable. And this is a quadratic equation modulo n. But you must be cautious about this operation. Divide by 2. We may not always divide by 2 if we work in modular arithmetics modulo n. We can only do that if n is odd. Then we can safely divide by 2 and get a single result. Otherwise, we may get 2 possible results. For example, if we take the remainder 4 modulo 6 and divide it by 2 modulo 6, we may get 2 possible results. 2 or 5, because 5 by 2 is also 4 modulo 6. So both results are correct. So you see, this operation is not a valid operation. It does not have a unique result, which means that it's not enough to know the remainder of this modulo n to check that this is true. But let's check if it's enough to know the remainder of this modulo 2n. Let's just try to change f by 2n and see what changes. If you open the brackets, the new terms that you'll get is 2n times this plus 2n times this and plus 2n squared. So every new term in the numerator has a factor of 2n times some integer. So the sum has changed by 2n times some integer over 2, which is equal to n times some integer. Which means that this whole sum has changed by n times some integer, which means that its remainder did not change. So we have shown that it's always enough for us to know the remainder of f modulo 2n to check if it's true. So if it's true for some f, it's also true for f plus 2n. And if it's true for this, then it's true for that. Which means that we can only seek for f from 1 to 2n. And that's exactly what we do in the solution. Let's look at the implementation. So nth is basically the smallest f for which the statement is true. Initially it's p plus 1. I try all the possible f's from 1 to 2n. If I have found any of the possible f that are less or equal to p, then I output yes, otherwise I output no. Now for the problem D, I will not retell the statement, you can read it now. Okay, so we have n strings of zeros and ones. First of all, we can of course solve for each string individually. We have to cut it into several parts, and m/2 of these parts have to be of length 1, and m/4 of those parts must be of length 2. Then we calculate the number of parts that contain at least one, and we need to tell what is the minimal possible value this number can get and the maximum possible value this number can get. Let's call those parts that contain ones good. So we need to find the minimal and the possible number of good parts. We can see that it's almost true that for every one there is a good part, and for every good part there is a 1. But for some good parts there are 2 ones. If you ignore the good parts, which consist of 2 ones, then it's true that for each part there is only 1, and for each one there is only 1 good part. So we can rewrite the number of good parts as the overall number of ones in the string minus the number of good parts that consist of 2 ones. We see that this part is constant. So the only part that depends on our actions is this. So let's just try to find the minimal and possible value this amount can reach. Okay, so in new terms, we have to pick m/4 non-intersecting pairs of cells, and then answer how many of them can be 1 at most and at least. Let's once again transform this problem and consider all the possible positions of those pairs. Let's call a position good if such pair would contain 2 ones. So let's for every position write if it's good or bad. This is bad, this is bad, this is good. So if you start a pair from here, it will be a good pair. This is bad, this is bad, this is bad, this is bad, this is good, this is good, this is good, this is bad, and this is an invalid position, so we don't write anything here. Now, you are allowed to pick m/4 positions, but you are not allowed to pick 2 positions in a row, because such pairs would intersect. So let's just ask ourselves, what is the maximum number of good positions that we can pick without picking 2 in a row? Well, obviously in each group of good positions, we start picking every second position, starting from the first. And there are 2 possible outcomes. Either we have reached m/4 good positions, and then we stop doing that, and say that the maximum possible amount of good positions is m/4. The other outcome is if we have reached the theoretical limit for the number of good positions, and it's still less than m/4 positions. And suppose we've picked g positions so far. We must show that it's always possible to pick the remaining m/4 minus g positions without taking 2 in a row. But let's just see that for each position that we've picked, there are at max 3 occupied positions now. So we still have m minus 3g free positions at least. So let's now again go through groups of free positions and pick every second position in each group. If the sizes of the groups are ai, we know that their sum is m minus 3g, and we've managed to pick ai/2 rounded up from each group, which is at least ai/2, which is at least m minus 3g/2. We have to pick m/4 minus g more free positions. Suppose we didn't succeed and this is less than m/4 minus g. As it is integer, I can write less or equal than m/4 minus g minus 1. Let's rewrite this inequality. So it turns out that G is strictly larger than M over 2, which obviously contradicts this statement. Which means the number of free positions that we've picked will always be enough to reach the total amount of M over 4 chosen positions. And thus we have shown that the maximal amount of good positions that we can choose among the M over 4 overall positions is minimum of M over 4 and the theoretical maximum amount of good positions. Now if we want to minimize the good positions, it's the same as saying that we want to maximize the bad positions. So we can apply all the same reasoning to the bad positions and get that the maximum possible amounts of bad positions that we can pick among the overall M over 4 positions is minimum of M over 4 and maximal theoretical limit for the number of bad positions. And the minimum possible amount of good positions among the overall M over 4 positions is obviously M over 4 minus the maximum possible amount of bad positions among the overall M over 4 positions. Now let's look at the implementation. So this function solve returns the answer for the problem for a given string. First of all, we count the number of ones. Then for each of n-1 positions, we check if it's good or not. Then we find the length of the groups of good positions and the length of the groups of bad positions. Here, if the position is good, then if it's the first position or the previous position was not good, then I need to start a new group. And then in both cases, I increase the last group by 1. Same for bad groups. Max good is the theoretical possible limit for the number of good positions. We take the length of the good groups, divided by 2 rounded up. We do the same for bad positions, and the answer is this. This is the minimum possible answer, this is the maximum possible answer. Then we find the answer for each string and sum it up. And finally, problem E. You can also read it yourself. So let's show the graph of auxiliary servers by pointing an arrow from server U to server AU for each U. What we get is some graph where every outer edge of each vertex is equal to 1. Such graph is called a functional graph, and it always has such shape. There's one cycle in the center, and a lot of trees that flow into that cycle. Or it can be several such shapes, but our initial graph was connected, so in our case it would be one such shape. Let's see what must be true in order for our criteria to be true. If we take one of the servers and start reaching for the auxiliary servers, we would get such a path. For every server from which we start, it must be true that all the other servers which don't lie on that path have a neighbor on that path. So this must be true for all possible paths. But each of such paths will end on this cycle. So maybe let's look at the cycle itself. If we start from a vertex which is a member of the cycle, the resulting path will be the cycle itself. And the criteria tells us that every vertex which is not on the cycle must have a direct edge into the cycle. So it obviously comes to mind that if this is true, that we can just always make each server to flow directly into the cycle. So we can assign this neighbor of the server which belongs to the cycle its auxiliary server. And after we apply this change, the resulting answer will look like this. Now it's obviously still true that from whatever server you start, the criteria will still hold. So we have shown that if the answer exists, we may always transform it into such shape, which means that from the start, we may have looked for answers only in such shape. And now the statement of the problem may sound like this. Find some cycle such that every vertex which is not a part of the cycle has a direct edge connecting it with the cycle. as the constraint for n is very low, we may solve it using bitmask dp. Our goal is to find all sets of vertices that form a cycle. In order to do that, we'll consider a process dp. The process will start in any vertex, and it will go into some vertex in which it hasn't been yet. If the vertex which we are currently at is connected to the starting vertex, then we may end the process here and call it a cycle. And the parameters of the process are starting point, current point, and the mask of visited points, because we are not allowed to visit one point 2 times. And the value of dp will be just true if we can reach such state and false otherwise. In such case, we'll have n squared times 2 to the power of n different states, and there will be O of n transitions from each state, because from each state we can go to any of the remaining vertices. But this time complexity will not pass the time limit, so we need to get rid of one of the n's. Let's notice that every cycle can be built by our process in several different ways. First, if we start from this vertex, go like this and end. Then if we go from this vertex like this and end. So there are many different paths of the process that lead to the same cycle. We may decrease the number of states of the process if we only allow to start from a vertex which has the smallest index on the cycle. Obviously, it will be still possible to build any given cycle with such process. But now we can get rid of this parameter, because the starting point is just the minimum vertex through which we've passed. And it's already ingrained in the mask, because it's just the lowest bit that is set in the mask. But now from a given state of the process, we can only go into the vertex which has an index larger than the minimum vertex we've visited. Thus, we have decreased the time complexity to n squared times 2 to the power of n, which already passes the time limit. And then we need to just consider all the possible masks that form a cycle and check for every mask if every vertex which is not part of the mask has a neighbor in the mask, which takes just n times 2 to the power of n. Now we can look at the implementation. Here's the function that takes the mask and returns the first bit of this mask. This is the adjacency matrix, and this is also the adjacency matrix, but in form of masks. So it's like adjacency masks for every vertex. This is the dp table. It's actually not just true or false, because in the end we will need to recover the cycle, and so we store not just true or false, but for every state we store the second to last vertex on one of the existing paths into such state, and -1 if such path does not exist. Normally this array would also just store true or false for every mask if it is a cycle or not, but as we need to recover the cycle, I also store the last vertex visited by the process that builds such cycle. The basic states of the dp, also known as starting states of the process, is when we are standing in some vertex and we have only visited it. For such states, I set the value to -2, which means that the path exists, but there's no second to last vertex on that path. Then I consider all the possible states of the process, starting from lower masks to higher masks. So suppose I have visited the vertices defined by this mask, and currently I'm standing in vertex I. And fs is the smallest index of the vertex which I visited. Then I fix a vertex where I want to go. Of course, it must be larger than fs. I check that it is not visited, and I check that it is connected with I. And then I say that one of the possible paths of the process into such state has I as its second to last vertex. Then I initialize the array cycle, filling it with -1s. And then for all the possible non-empty masks, I check if this mask contains only one element, I skip. because the cycle must contain at least 2 vertices. Then I check for all the possible ending vertices. If such state where this vertex is the ending vertex is possible, I check that I can go from the ending vertex to the starting vertex. And if it's true, then I can build a cycle with such mask. And the ending vertex on the process that builds such cycle is I. Then for all possible masks which form a cycle, I simply check that all the other vertices have a neighbor inside the mask. And if it's true, I recover the cycle. And then for every vertex on the cycle, I set the next vertex on the cycle as its auxiliary server. And then for every other vertex, I find its neighbor which lies on the cycle and set it as an auxiliary server to this vertex. And then I'll put the answer. That's it for today. Thank you for watching, and I remind you that I give private lessons on competitive programming. If you are interested, contact me on Telegram.